Okay, so what I want to do today is I want to talk about some numerical techniques. So I want to talk about finding candidates for extrema, and there's another application of finding eigenvalues. And if you're interested in stuff like this, there's two really entertaining papers. Do dogs know calculus? Do dogs know bifurcations? I actually have met or at least one of the authors of these papers, and I actually even met the dog who we got to come to Williams. Fascinating problem. We'll talk a little bit more about that. So why in a class on the mathematics of sports do we care about numerical techniques such as trying to find candidates for maximum and minimum? So again, it's interesting, with the ability of the web, you can search for almost anything. Here is a picture of a 4-person outfield. Now, the number of fielders that you have is a constant. So if you have 4 outfielders, what can you immediately tell me? Yeah, or you have at most 3 infielders. You can't have somebody backing up the catcher because you can't start off in foul territory. But so if you are doing something like this, you are shifting someone away. And so in this situation, they've basically given up on the left-hand side. Although interestingly, they have somebody even deep in left field. And so there's a lot of interesting things that this can lead to. A couple of years ago, I supervised a thesis at Williams on outfield shifts, just how you want to optimally position your outfield. One of the things that's being done now is they have changed the rules of baseball so that you have to have 4 people start in the infield, at least 2 on each side. So you can have your shortstop starting just, on the third base side of second base. And if you want, as soon as the ball is thrown, they can start moving. And you can have your third baseman, shift over as well. So you can create, a shift like this. And then what they do is they move one of the outfielders to, right into shallow outfield. And this is very similar to the shift that was done before, where they would move maybe the second baseman over there and the shortstop would move over there. Why do you think teams are willing to do this defensively?
He probably doesn't do it the other way that often.
So the hope is that the batter is not going to hit it to the left side of the field that often, especially maybe even into the outfield. But it's a trade-off. So as a hitter, what do you need to learn how to do? And again, in the old days, you would sometimes have absolutely nobody on the left side. What do you need to learn how to do as a hitter? Hit the other way. You don't have to hit the other way as effectively as you would hit in general, or just learn how to lay down a bunt. If you're fast enough. There are some players where they basically need the home run to be able to get to first safely. But for most people, if you can lay down a good bunt to the left side of the field, if there's nobody there. And so this is a really interesting optimization problem. You have a fixed number of fielders with a fixed probability of converting balls hit to their regions to outs. How should you stack them? And then what makes the game a little bit more interesting is that Major League Baseball can put rules and constraints on how you can do things. So you can solve the problem as a pure optimization problem, and then you can start putting in constraints. Now Major League Baseball says I have to have all of my initial configurations satisfying the following constraints. So this sounds a lot like almost like Lagrange multipliers and stuff like that, constraint optimization for multivariable calculus. Normally we do, say I have a sphere and I want to figure out where's the function largest on the sphere. You could actually have, maybe the function is on a 12-dimensional surface, which is the intersection of a 15-dimensional surface and a 17-dimensional surface. And now you have a more involved Lagrange multiplier problem, which is normally not done in the first class of multivariable calculus, but there are techniques for that when you have multiple constraints. And it turns out it generalizes very simply. And rather than saying I want the gradient of f to be in the direction of the gradient of g, I want it to be in a linear combination of all the different gradients. So there's a really nice generalization of this. And so for whatever problem we have, so let's consider the motivating example today, the location of fielders. And we want to figure out what is the optimal way to place them. So what inputs come in? And again, in a class like this is what I care about, is how do we set up the problem? What are we going to try to do? And then how can we use math to help us answer this? So what is the problem we're trying to solve? So, I'm trying to put my outfielders. We will assume that the infielders have to be fixed. We'll assume you have no freedom in terms of how you place the infielders, just to make the problem simple. We have the ability to put our outfielders. What are we trying to maximize or minimize when we decide where the outfielders will be? Yes.
Maximize the chances of an out.
So that is one possibility, is that we're trying to maximize the chance of an out. That may not be the right thing to do, though. What else could we do?
Minimize hits.
One is we could be trying to minimize hits. What else could we be trying to do?
Minimize runs scored by the other team.
Could be trying to minimize runs scored by the team. No one has said the statistic I like yet.
Maybe reduce slugging because you don't want you want to play deeper, give up doubles.
These are all reasonable things, but these are not what I'm looking for. Probability of winning, right? At the end of the day, do you really care how you win? Now, a lot of you do fantasy sports and you have your leagues, and so yes, so it's not enough to win. I want my player to get all the points because I want to beat the other people in my pool. But if you are managing a team, what is your objective? Your objective is to maximize your chance of winning. So you look at not just minimizing hits or maximizing outs or decreasing slugging. These are all great indicators of the statistic we care about. At the end of the day, it's always about, I want to increase my chance of winning. What is going to do that the best? So for example, what if I do a strategy that 99% of the time will get the batter out, and 1% of the time, well, let's see, even more ridiculous, 99% of the time will win the game, and 1% of the time it's going to lead to a bad play, which is going to mentally destroy my players, and we're going to give up 2,000 runs. So in a ridiculous situation like this may not be minimizing the average number of runs allowed, but it would be maximizing probably my chance of winning. And so I'd be quite happy to have a situation where, look, if I'm going to lose, I'm fine with the blowout. I want to just increase the number of times I'm going to win. This is more prevalent with younger kids playing. And, I still remember, a championship series where I was coaching. We had to win 2 out of 3. We just had to win the final game. I think we were up 12-3 in the final inning. And we win, I think, 12-9 with a lot of runners on base. The initial batter who started the inning was out. We got him at first. I don't care that this is being recorded. The umpire called him safe. The parents were furious. The parents started saying, and I had to keep the parents calm because you're not going to change the umpire's mind. You're going to just piss him off. But it rattled our pitcher. And our pitcher then started muttering things under his breath, and the umpire had to yell at the pitcher, and things just escalated from there. We won the game. I go, it's a 9-1 lead. We got to be able to hold a 9-1 lead for half an inning. But I know 2 or 3 times like that with young kids where something like this happens and it just goes a train wreck, that the team collapses and lets up a huge number of runs. At the majors, it's hopefully a little bit better than that. But it's always, always, always think about what your objective is. And so many times people focus on the wrong statistic. They focus on things which help you get to where you want to be. We want to get to maximizing our win percentage. So my favorite statistic is win probability from each configuration, from each game state. So I can look at each hitter who's up, and then I can try to calculate what is the win probability before and after for various outfield configurations. So what information do you think we'll need to figure out how to position our outfield? just to give you a sense of, how bad this was, and, especially anybody who's not a senior who's looking for possible thesis topic on applied math, we started this, but we did not finish the project. What would you need to know to deploy the outfield?
Like win percentages or run expectancies for each kind of condition.
So we would need that for each game state, because it doesn't matter where the people are in the field. I just look at what's the win percentage for this configuration before, what's the win configuration afterwards, win percentage afterwards. There are a lot of websites that do this, and they assume an average batting order from that point onward in the game. They just look at how many times in Major League Baseball, for instance, has a home team been leading by 3 runs in the top of the 7th with runners on first and third, 1 out. And they look at all the times this has happened. They look at how many times the home team has won, and they use that to estimate the win percentage. It is not perfect, yes.
Do you not factor in like how good the team is? Like if
So the standard websites you go to do not factor that in. They just say, we looked at all Major League Baseball games that had the home team leading by, I think I said 2 runs in the top of the 7th, runners at the corner, 1 out. And again, that's a very easy calculation to do because you can just cull everything together. A much better calculation would be to then factor who you're playing. If you're playing a team that is strong offensively, then that 2-run lead is not nearly as good. Let's say now it's the bottom of the inning. So you're up by 2 runs, you have runners on first and third. If you're playing a team that's weak offensively, you might say, I might be willing to sacrifice an out to get that runner from third home because we're playing a weak team offensively. And I think if I have a 3-run lead, I can nurse the 3-run lead. And so I might be giving up the chance of a big inning. But it might be better for me to have the guaranteed run come in than to risk getting nobody that inning. So it's a absolutely great question. We will assume that we have a black box that will tell us the win probability of any configuration. So what do I need when I'm trying to figure out where to put the outfielders? So I need to know where the batter hits the ball, but just knowing where the batter hits the ball is not enough. What other information do I need to know about the hit?
Like a density chart of not just where he hits it, but how frequently he hits it to each of the spots.
Sure. So one is where they hit, how often they hit there, but I need more than just that. Trajectory.
like how high the fly ball.
I'm sorry? Right. So what I really care about is time to get there. Where does it land? And so if it's a very high pop-up, that gives me enough time for the fielder to move. Whereas if it's a line drive, then I've got to be able to get there much faster. Now they have this data. When I was a kid, we did not have this data. We have this data now. This is a doable problem to figure out what is the hitting profile of each batter. To make things simple, we can assume that a hitter's profile is independent of the shift on them. That's not true. And so a good hitter will adjust a little bit what they do based on the defensive configuration. But we'll assume that that's a low order effect for now, just to keep things simple. Do you think you have enough data for a hitter in Major League Baseball to give the information to the model? Is there another variable that might be important when trying to figure out how the hitter hits the ball? Okay, well, we'll know that about the hit. That, again, we don't care if they're lefty or righty, we just care how they hit. But there's something related to that, though. When you're trying to figure out how the batter hits, there's something else that really matters.
What kind of pitches they're hitting?
What kind of pitches they're hitting? So who's the pitcher? So you might have very different profiles depending on the pitcher on the mound. There are some pitchers who are much more likely to induce ground balls, others who are much more likely to induce pop flies. So if I'm looking at data, I might break my hitter's profile based on what kind of pitcher they're facing. And so I take all the at-bats and I classify it. What else might matter? And again, some of this, you do need a little bit of knowledge of baseball. If you don't know baseball, that's fine. What else might change how a pitcher pitches?
Well, you could pitch differently according to the shift.
You could pitch differently according to the shift, but there's something else.
How many pitches he's already pitched?
So one could be how many pitches he's pitched, if he's getting tired. Could be also if there's runners on base. If there's runners on base, there's the ability to steal the pitcher's catcher's communication and signals. The pitcher has a different windup if there's runners on base. And so because of that, there is a difference in hitting profiles depending on the game state. So again, when you're doing problems like this, always keep it simple. You might say, let's just assume it's the start of an inning and just try to configure what's going on in a situation like that. So there's no base runners, standard pitching. So what we might want to do is we need to get a lot of data. You might not have enough data on one hitter with certain types of pitches. So what could you do? So I want to try to establish a profile of, say, my hitter against a knuckleballer who's on the mound. And there's not that many knuckleballers in the league. And so my hitter's not going to have that many data points. What could I do to try to get more data points? I'm asking them to just meet after the game and do 1,000 is not an option. This is the problem you're going to face when you leave Williams. You're not going to have all the data you need, so you have to justify increasing your data set.
Yeah, I don't know how many knuckleballers there are in the league, but some grouping together pitchers maybe.
So you could group together pitchers, but not only grouping together pitchers, grouping together batters. And so what you could do is you could say which batters are similar. And so we could say this batter has a very similar hitting profile to so-and-so. We're going to group all of their at-bats together, get a larger data set and say your right-handed power hitter, a little bit overweight, and get more data like this. I did stuff like this with my senior thesis. I was looking at energy levels of heavy nuclei, and you don't have that many data points. So you start to say, well, these heavy nuclei have very similar quantum numbers in these key categories. We think they behave pretty similarly because their outer shells are similar. And so we're going to amalgamate that together. And this is one of the things you often have to do to get enough data to proceed is we don't have enough data to start. So we're going to find things that are similar and put them together. And so now I'm going to have a bunch of batters that I think are similar. One of the best honors you can have in baseball is to be elected to the Hall of Fame. And it's always controversial for some players as to, should they make it or should they not? Bill James, who is the father of a lot of baseball statistics, he has a similarity index where given any two players, you can calculate how similar you are, who are the players you have most in common with. If the people you have most in common with are all Hall of Famers, this is a strong push for your case. If you are similar to people we've never heard of, then, well, maybe this is not really a Hall of Fame candidate. So, again, to just get the data to do the problem is often tricky. And we can frequently do this by, only amalgamating things. All right, so now let's assume we have the data and we have configurations and we want to try to figure out what is the best configuration of the outfield. Well, one of the things we can do is let's assume, I'll assume something like this. And I have to choose where to put my three outfielders. So, it'll be P1, P2, P3, and we'll call this, O for the outfield. And so what I might want to do is I might want to maximize over all pairs P1, P2, P3 in O cubed of maybe my win probability with that configuration. Does everyone agree that this is the problem I want to do? And so this will depend on who the batter is. So this could depend on the batter and the pitcher and maybe the games, all stuff like that. And so for a given configuration that comes up, I want to maximize my win probability or my change in win probability. So maybe it's a delta. And then I have to vary P1, P2, P3 over this entire region. So how would we do this? Does anybody know techniques to allow us to do something like this? Can we just evaluate it at every possible position? Why not? There's uncountably many. So there's a couple of approaches. One is a grid search. I could make a grid of all possible points. And I could say that all of my fielders have to start at a grid point. And now it's a finite problem. And you might even have some rough idea. Maybe P1 has to start off in this region, P2 has to start off in this region, P3 has to start off in this region. So I might know enough like that, and I just want to search and tweak those a little bit. And so the more refined grid you have, the better the answer. But at some point we have to ask, do we really have data that's so good that we want to have the good points differing by, 1/10 of an inch? Yeah, we probably do not have data that accurate in terms of the hitter profiles. So in terms of you're trying to figure out what scale do we want to look at, it's probably not going to be on the scale of inches. Might be on the order of feet in terms of just where we want to put people, in terms of just how good is our data. And we have to estimate what's the probability of converting various balls in play into outs. But here is one possible way of trying to solve the problem. Is we can do a grid search. So is everybody comfortable with trying to do this with a grid search? All you do now is you just have your computer, while away. It's not that hard to program. The difficulty is that, unfortunately, it could just take a long time. So what you do is you do a very coarse grid first and get an answer there. And then you refine the grid, and then you refine the grid, and you might focus on certain regions. Says, look, it is unlikely that the optimal configuration is going to be having the 3 outfielders having a Congress, all the way down here. So I can focus my energies in certain regions. So this is just something that should be in your powerhouse of techniques to solve problems. Write down a formulation, write down what you're trying to optimize, and then just brute force it to death. This is the 21st century. We can do this. The difficulty, of course, is coming up with what is this function? Well, this is coming from the game states, and then calculating the change, we need to know how likely the batter is to hit the balls into different areas, and then say, if the batter hits the ball over here, what's the probability I turn into an out? What's the probability it's a single, double, triple, and so on? And depending on what runners are on base, what's the probability that a runner from first maybe moves to second, moves to third, scores, and all that. That's the baseball specific part of this. But the general part, which I want to just get through today, is just we do a grid search. The other one is, continuous gradient approach. So even though we know we are not going to be accurate to within 1/1000th of an inch, let's assume we can put our outfielders anywhere we want. And then for each configuration, we can say, let's calculate what the value of this is, and then let's see how we should move things. So one of the things, how many of you have ever heard of the greedy algorithm? who has never heard of the greedy algorithm? Okay, wonderful algorithm. It's basically described as essentially at each moment in time, do what's best. You know, I'm going to just take the best available alternative. And I'm going to keep doing the best available alternative. And the hope is that the greedy algorithm will lead you to the optimal. If you do the best alternative at every moment in time, that should lead to the best possible outcome, right? What is your goal in life? Well, if not your goal, what do you think someone's goal in life might be? Yes.
Make as much money as possible.
So is that your goal? Is to make money?
Not mine necessarily.
No. But I'm saying, do you think that's their goal?
Not actually, I'm saying it could be.
Okay, but why do they want the money? So is it the money that they want? Happiness. So, you know, again, it's what's the correct statistic to look at? Are you trying to maximize money or are you trying to maximize happiness? I think happiness. How can you maximize happiness? Make a lot of money. And so if you make a lot of money, you know, you can then be very, very happy. So does that seem reasonable that the statistic we really care about is happiness? One way to get to happiness is to make money and remember the people who helped you get there, right? So how do you make money? Or what do you do to be happy? Can somebody give me an example of either? Get a job. How do you get a good job? Internships. How do you get a good internship? Do well in school, know people, use your network. Right? We've had classes where people have come down and have told us about how knowing people can lead to getting good jobs and whatnot. Right? So you want to do well in your classes. You want to do well in your social interactions with people. Does anybody do things other than classwork on campus? Okay, so people are not, oh, I wish I'd asked this early in the semester. Okay, so you're not spending your entire time outside of classes preparing for classes. So you're doing activities that you enjoy. Why don't you do more activities that you enjoy right now? Why doesn't everybody just get out of this class right now and enjoy the glorious day outside? It's always risky doing that. I don't know if I would do that with Frosh. There is the story of somebody who was at a school where they had a Calc 1 final, and a bunch of older math majors showed up and said, "This exam is unreasonable. I refuse to do this. Who's with me?" And a bunch of people just walked out, and they were all seniors, not in the class, and they got a bunch of Frosh to just walk out and protest. And so the department was not amused, but they had no idea who was behind it. No, it was not me. I did other things. So why are you here? Because if you want to maximize happiness, is there something you could do right now that's more enjoyable than this lecture? I'm not going to be insulted, okay? No one likes to kiss ass, by the way. Why are you here? Why aren't you maximizing your happiness locally?
Because not being here and, I don't know, losing a participation grade might also impact happiness.
Or maybe that's something that could be useful later in life. Right. I'm going to have to really edit today's lecture online. But there are so many times you are choosing not to locally maximize happiness, right? When you went through high school, a lot of high school is getting you ready to get into a good college. And so there's a lot of things you did in high school, you might have done in high school, that you did to maximize your chance of getting into a good college that you may not necessarily care about, but it looks good on the CV, it looks good on the resume. The reason I'm really emphasizing all of this is to put you in the right mindset to look at the greedy algorithm. Doing what's best locally is not always going to lead to the best answer. There's the danger of getting caught in a local maxima or local minima, that you get caught in a local extrema. That if you're doing what's best locally, that doesn't mean you're going to necessarily reach the global. So for example, let's say I have a mountain range like this. And I'm over here and I want to go to the highest point I can get to. And so what I decide is that every moment in time, I'm going to walk in the direction that increases my height by the most. So if I do that, I'm going to just flow up like this and I'll land over here and I'll stop. And I'll end up at a local maxima. That's the danger for something like this, is that you could end up in a local maxima and not a global maxima. There's actually an interesting way around this problem. Anybody know a way around it? So I start at some point, and I just, at every moment in time, I do what's best.
Run it at a bunch of different.
Yeah, run it at a bunch of different starting points. So now, if I start over here, I run it and I get to this point. If I run it over here, I'll get to this point. But if I start over here, I just need to get lucky once. I'll now run and I'll get to this point. So multiple starts. So if I do multiple starts, and for each one of them, I look and see what's the best I get under the greedy algorithm, then I take the maximum of all of those. And the hope is that if you take enough of these, you'll actually end up at a pretty good place. But there is a huge danger in getting caught in a local optimum. And when we're looking at the outfield, we have some intuitive sense of where we want to put fielders. I don't want to have a congregation of 3 outfielders in the far deep left. And so I have some initial sense of where I want people to be, but maybe that's wrong, and maybe I end up with a slightly wrong place. All right. I think the last class we talked a little bit about Fubini's theorem and multivariable calculus, and so let's just continue. So I'm convinced that there's absolutely nothing that was remembered from multi. Do people remember Lagrange multipliers?
I saw it. Maybe. I don't think it's off the top of my head.
When I was teaching for the first time at Princeton, we had a student who failed the police lineup where they could not identify their instructor if their instructor was in a lineup. That's how often this person went to class. So Lagrange multipliers. So we have a constraint, say, g of x1 through xn equals c. We have a function f of x1 through xn, and then the candidates for max min of f for x1 through xn on the surface satisfy the gradient of f is lambda gradient of g. And remember, so this is df dx1 equals lambda dg dx1 ... and g of x1 through xn equals c. So we have n+1 equations, n+1 unknowns. So we expect to be able to solve this and have a finite number of candidate points. What's really going on is if I have my surface, here's my surface, g of x1, xn equals c. The gradient of g is basically equal to the normal to the surface. If I give you the gradient of f at some point, I can represent the gradient of f as some component in the direction of the surface and some component, I'm running out of colors, and some component normal to the surface. And so what does it mean for the first derivative to be positive? If the first derivative is positive, it means you're increasing to the right and decreasing to the left. So the only chance you have, if you're not at an endpoint, to have a maxima or a minima is the first derivative has to be 0. So if you look at what's going on here, what we're really looking at is directional derivatives. I want my directional derivatives to be 0 to have a chance to have an extremum. Because if my directional derivative is not 0, then just walk in that direction. So you look at any tangent line to the point you care about on the surface, and I move a small amount in that direction, and I calculate the directional derivative. If the directional derivative is not 0, then I can't be at a maximum because I'm getting large if I go in that direction. I can't be at a minimum because I get small if I go in the other direction. So the only chance I have to have a maxima or minima is my gradient of f has to be in the same direction as the gradient of g, so that no matter what tangent direction I take, as I keep walking on the surface, my directional derivatives are all 0. That doesn't mean that I have a maximum or minimum there. It just means that's where my candidates are. Does this seem vaguely familiar? So this is Lagrange multipliers. And what a lot of people forget when they see Lagrange multipliers is they think, the gradient of f equals lambda gradient of g. They tell you which direction to go. I've got to have my gradient aligned with the normal if I want to have a candidate. But you can also look at this another way. Imagine I'm not at a place where the gradient of f is aligned with the gradient of g. So I know I can't be at a maximum or minimum. The gradient of f is saying, hey, if you want your function to get larger, move in this direction. If you want your function to be small, if you want to move towards a minimum, multiply by -1, move in the opposite direction. So this is usually not emphasized when Lagrange multipliers is done, that you can use the gradient to try to figure out how do you find the maximum and minima. If you're at a place where the gradient is not aligned, the gradient of f is not aligned with the gradient of g, it's telling you which direction to move. Okay? And so we can use this to flow and try to find where we are. But the danger is that you might end up in something like this. You might find a local maxima or local minima. So one way around this is you just try a bunch of points. And we'll probably not reach that today. We'll probably wait till Wednesday to do that, because we're going to use Monday as a day to discuss topics. If you're fine with your topic, no need to come on Monday. But if you want to talk about how your final project is going, I'm just blocking off Monday because I know people are working with other people. This is a busy time of year, and trying to find a time when everyone's schedule aligns is challenging. I know everybody is free from 10 to 10:50 a.m. Okay. So I'm now going to give one of my favorite problems, do diagonal calculus. And so here, here's the water. Here's the land. And we have a guy over here in the water. And we have a dog. And let's say you throw the stick over here. And here's my dog. What path should the dog take to get to the stick? So let's say I throw the stick over here. What path will the dog take to get to the stick? Yes, from straight line to the stick. I was about to say, maybe you can take some frosh later today and go down to the Hoosick River. No. All right. What if I throw the stick over here? What path will the dog take? Straight line. This is not how about. What if I throw the stick over here? Straight line, right? What if I throw the stick all the way down over here? What do you think? So the dog might decide to travel like this. I'll use a different color. I'll use the purple color here. So the question is, which is a better path for the dog? If the stick is thrown close to the dog will swim straight for the stick. But if the stick is thrown far away, is the best path to swim to it? What do you think?
Depends how much slower you swim.
Okay, so do you think you swim at a close to the speed that you run on land? No, so the dog is much faster on land. So this is a great example of where the greedy algorithm can fail. What is the dog doing when the dog swims directly to the stick? The dog is solving the following problem. At every moment in time, I choose to do what will decrease my distance to the stick by the greatest amount at that moment. I am doing what is locally best. For many things in life, this is not a bad strategy to do what is locally best. Given that you're all at Williams, this is a strategy you have chosen not to follow in many aspects of your life. You know, if we assume that your goal is to maximize happiness, you are choosing to do other things. So the question is, when is it worth doing something else? When is it worth taking a hit? And then long term, it's going to pay dividends because it gets you to a better place. The faster the dog swims on land, what can you tell me about this angle? Yeah, it gets closer and closer and closer to going straight down. You know, if you imagine the situation where the dog is infinitely fast on land, one hell of a dog, the dog would want to get to land as fast as possible because there's no cost for them going along land. So you can actually solve in the real world and figure out what is, you know, the angle that you would come in on, what is the critical tipping point when the stick is now far enough away that you would actually rather swim to land. And there'll be a critical place where it's going to be indifferent. You know, you're indifferent between going straight to the stick and going to land. And then if you push it just a little bit farther, you have wildly different behavior. And so it's fascinating when you look at the distribution of the optimal path that the dog takes. The optimal path that the dog takes is very continuous as I move the stick close to the dog and start moving it further away. The paths don't change that much. And then all of a sudden there's this critical point where as soon as I move the stick past that, the path the dog takes changes fundamentally. All right, so let me see if I can actually do it. So we'll assume the water of the dog is 1 meter per second, and we'll assume the land of the dog is infinite meters per second. So there's no cost for the dog to swim, to run on land. So let's imagine that the dog starts here is the dog, and we'll say that this is X, and we'll say over here is the stick, this is Y. And I want to figure out what is the critical distance, oops, what is the critical distance so that I'm indifferent between the two paths? How far away does the stick have to be? Does everybody understand the problem? Can somebody tell me the time on the water? And we need some notation for this. Let's call this maybe L for land. How long do we spend in the water? I'm sorry?
X plus Y.
Nope. So time on the land is going to be X plus Y. Sorry, there's 2 different times of water, sorry. Time, let's call this the water route, and this will be the land route. So I should really then use gold here, sorry. So the land route is the route where I'm coming down to the land. So I wrote this in a very confusing manner. So for the land route, I go X then I have no cost for being on land, and then I do y. So that would be x plus y. So for this one, I should really be using red. What's that time going to be?
1 minus the square root of 1 minus x squared plus l squared.
Okay, so for the water root, this distance over here is y minus x, this is L. So that's going to be the square root of L squared plus y minus x squared. So does everyone agree that those are the times for the two different roots? And I want to set them equal. So hopefully you've seen this in calculus before. Never, ever, ever work with a square root if you can avoid it. So rather than setting the times to be equal, let's set the square of the times to be equal. So we would have L squared plus y minus x squared equals x plus y squared. So L squared plus x squared minus 2xy plus y squared is x squared plus 2xy plus y squared. So the x squareds and the y squareds cancel. And we get L squared is 4xy, or L is 2 times the square root of xy. Okay, so if we take that to be L, they're going to be equal. That's the critical threshold. Does this remind anybody of anything? Need some pure math for this one. So what's going to happen if L is greater than 2 square root x y? So if L is greater than 2 square root of xy, what do we know? It's faster to go on land. Then land is faster. Okay. So if land is faster, then we know the water route is taking more time. So the water time is greater than the land time. The land time is x plus y. Wait a minute, am I getting things phrased wrong? So I want to make sure I do the algebra correctly. Right, so the longer L is, the better it is to do it on land. So the land is going to be smaller. And so all right, I'm going to stop here because I'm going to get it wrong, sadly. But we have the square root of xy and x plus y floating in this problem. I think this goes back to something we did in the first day or one of the first weeks of the class, the arithmetic mean, geometric mean. Did we talk about that statistic? It's basically looking here right now that there's a way to get from this that x plus y over 2 is greater than the square root of xy. I'm missing it right now, and I don't want to do the algebra improperly because it's 10:50, so I'll send that later. All right, enjoy the rest of the glorious day.